Hi, for a while now I've been thinking about building a robotic arm. I had a rough idea of what the mechanics would look like, however I was less certain about how to actually control the arm. Meaning how many signals do I need, what kind of motors I would end up using, and what kind of communication should the whole system run on. And this quickly turned into a bit of a chicken and egg problem, as I wasn't sure what I would need in terms of number of stepper drivers, servos, as well as auxiliary inputs and outputs. I couldn't design around a specific controller. But without knowing the controller, I also didn't know what the arm could be capable of. Basically, as I wasn't sure what I would need, I wasn't sure what I wanted. And so in the end I decided to start this whole project by building a control board myself, something I can develop and iterate on as the project gets more refined. And so in this video I want to highlight the process of me prototyping a fully custom control board, show what worked and what needs improvement. So this build does need a bit of an introduction. I want to keep it brief while still trying to convey my thought process. Starting with the very first sketch of what this control board might look like. I asked myself the question, what kind of outputs do I actually need? Or what kind of functions does my control board need to have in order to move around and interface with a robotic arm? And these functions I narrowed down into 3 categories. The first one are step and direction outputs for external stepper drivers to move a joint or axis. Second are PWM signals, which let me drive things like RC servo motors or variable speed components such as a fan or other small DC motors. And finally, digital switchable outputs for things like solenoids, small valves, or anything else that just needs an on and off signal. So 3 types of signals without yet knowing how many of each I would need. To handle these outputs I ended up choosing the RP2350 microprocessor, which for version 1 of this build is part of the Pico 2 development board. This board should have plenty of GPIO to let me play around with different configurations. With these 3 types of outputs in mind, I then looked at a soft or firmware that can run the actual controller. And I quickly settled on GRBLhal as it's flexible, has a lot of built-in functions, and it lets me customize the board configuration to match whatever I/O that I end up needing. Here the bigger picture is that I want to use a version of the Robot Operating System or ROS to do the motion planning, and then let ROS communicate with the controller via something like a USB connection. But this is something for later on. So this is where the project then actually started, taking the base GRBLhal setup and modifying it while testing the different outputs directly on the Pico using a G-code sender and my oscilloscope. The step and direction outputs were the most straightforward. I set them up so they were handled by the PIO state machines, which was one of the main reasons I chose the Pico 2 in the first place. The PWM signals are implemented in 2 ways. The first one is a 50 Hz servo PWM, so your classic 1 to 5 millisecond signal used for RC servos. This one runs through a plugin and uses the M280 command. As well as a true duty cycle PWM right now running at 5 kHz, which is useful for small pumps or DC motors. This one uses the M68 command. Each of the PWM output channels can be driven by either of those modes. It's not fully hot swappable, so a quick board reset is needed to switch between those modes. The last type of output is the digital on-off function. This one I implemented using a small custom plugin, now using the M281 command. So with all of this tested on a Pico, I know that the microcontroller can handle all the signals that I want and that I can customize the setup later if needed. And all of that basically only limited by the number of I/O of the microcontroller. So once I knew that I can implement the in and outputs that I need, I then started with the actual controller. And this is by far the most involved board that I've designed for one of my builds. The layout is mostly based on a reference design of the different ICs that I'm using, with the main goal of keeping the microcontroller isolated from anything that could potentially damage it. I will go briefly over the main sections of the board, but skip a lot of the finer details. If you want to have a closer look, I will put the files on my GitHub, or you can ask away in the comment section. So this is what the current controller looks like. It's powered by a Raspberry Pi Pico 2 and I've added a 12 volt as well as a 5 volt DC to DC converter to supply the different sections on the board. Feature wise it includes 5 differential step and direction outputs, 3 PWM outputs, 3 solid state relay outputs, each good for around 1 amp, 7 inputs for homing switches, limits and e-stops, and both UART and USB connection. For the board design I started with the power section. The idea was to generate clean 12 volt and 5 volt rails from the main 48 volt supply that the motor drivers will eventually run on. This way I only need one external power supply for the whole robot arm. Both converters use the same IC and should be able to supply around 2 amps, which should be plenty for all the outputs. Many of the larger stepper drivers expect at least 5 volt on their logic level. So every channel first goes through a digital isolator to both shift the level and protect the microcontroller. Right after that I added a differential line driver, which should help a lot with noise immunity and longer cable runs. The Pico with the RP2350 has a lot of built-in PWM capability, so these signals come directly from the microcontroller. Each PWM channel again goes through a digital isolator and then into a MOSFET driver. That way I can use these outputs for a range of different components, without worrying about overloading the microcontroller pins or the isolator. To make the board even more flexible, each of the PWM outputs can be driven by either 5V or 12V, which can be selected with a jumper. And if you can spot what I've missed in this version, you're already ahead of me. And for the higher current on-off functions, the relay output signals go directly into optically coupled solid-state relays. They're simple and they keep the microcontroller isolated from whatever load that I end up switching. The inputs follow a similar idea. Each of them is routed through an optocoupler before reaching the Pico, which keeps the logic side protected if something goes wrong on a limit switch or an e-stop line. So with that, all the inputs and outputs should be in the correct voltage level and properly isolated, which should reduce the chance of me actually frying the Pico during early testing. And after going over the design a couple more times, I ordered my first test batch and got everything together to see if it actually works. But before anything else, let me quickly explain why I decided to hand solder the entire board and not have the manufacturer assemble it. And this is for 2 reasons. The first one, and the most important one, is that I wanted to be able to test the board in sections. So instead of having all the components soldered from the start, I wanted to place only the parts in one subsystem, be able to test it, confirm that it works, and then move on. That way, if something fails, it fails in isolation and doesn't affect the rest of the board. And the second reason is cost and waste. If there's a design issue, and in a first prototype like this there usually is, I don't have to throw away dozens of components that were soldered unnecessarily. This approach keeps the damage relatively small if I have to make changes to the design. However, the downside is that this approach takes a lot of time. Even just a board like mine has over 16 visual components and over 150 overall parts. I spent hours tracking component inventory, placing tiny ICs, and making sure that I don't mix up any values. But for a prototype like this, it's worth it. Once the boards and components arrived, I focused on the 12V and 5V converters first. This is one of the more important areas to test individually, as if anything goes wrong here, the rest of the board won't even start up. For me, PCB design, the component selection and sizing is still quite new, and I worked on and off for about 4 to 6 weeks on this board. So I was quite anxious to see what works and what needs improvement. Okay, it does seem to work. At least all the LEDs light up and nothing catch fire. I'm completely amazed by that. I don't know if the voltages are correct, but at least according to the LEDs, it should be in the right ballpark. But yeah, nothing blew up. I'm so happy. This is just amazing. I thought this would be like the first issue, and then I would have to redesign the board or parts of the board because nothing works. I still have to see if something overheats over time, check temperatures and stuff like that, clean it up a bit. But I'm stoked to bits that it just worked. First try. While testing the output voltages, I noticed that the 12-volt output wasn't shown correctly. However, 5-volt was. As the layout is identical, the issue could not have been something major. And as it turned out, after reflowing all the footprints, 12-volt worked as well. A bit lower than I would like with 11.85 volt, so I will have to tweak the voltage converter that sets the output voltage in the future. As I'm using a hot plate, I will try not to place any through-hole components during testing the different sections, as this would make further soldering with the hot plate a lot more difficult. Here, a hot air soldering iron or even a reflow oven would be a great upgrade. This hot plate was the cheapest I could find on eBay, but it still functions just fine and gives me a great place to start. So after applying solder paste and then moving the board onto the hot plate and making sure that all the pins got enough heat, I then powered up the board. Well, that was a bit more explosive than I hoped. I think both chips are done. I was pretty sure to check the orientation, and I pulled it up. You have two rows. The bottom row is your low voltage input, and the top row is your low voltage output. And this is also the way I place the low voltage on the bottom and then higher voltage, so 5 volts at the top. And looking at my view here on the right, it looks like it's correct, at least as far as I can tell. So to hopefully not get the exact same issue again, I will first just solder the digital isolator and then check for resistance before soldering the second IC. So it doesn't seem like it's shorting out. I don't really know what else I can test. I don't want to say that it was just a fluke, because that would be kind of boring. Should I just power it up? I mean, there is another chip, but honestly, it's not shorting out. I think I had a brain fart. So I just wanted to connect the power supply back to it and put ground on this location, and then noticed, wait, that's the 5-volt input, or the 5-volt output, to be honest. And I thought maybe that happened the last time that I plugged in that board. And I checked the footage, and I did. So it wasn't this IC fault, it wasn't also that IC that faulted. I just supplied the 5-volt rail with 30 volts. 3, 2, 1. No explosion. That's great. That's great. Now I'm wondering, how did you survive? I mean, I didn't solder it to the board, I just placed it there. But I don't think that you should survive 30 volts. Okay, so this looks a bit more janky than it really is. I've rigged up the Pico so I can connect it to my board. I've connected the x-axis to my scope, and I'm controlling the Pico with the Universal G-code sender, and from here I can send commands to the version of GRBL that is running on the Pico. And so if I now send a X command, so an X movement command, we are able to see it on the scope, sort of the step or the pulse cloud coming in
increasing frequency during acceleration, then staying constant, and then decreasing again during the deceleration phase.
The PWM outputs were next, so I again applied paste, placed components, and then soldered these components. I then rigged up the controller to test the output functions.
Alright, now I'm sort of checking the path of the signal, and you can see coming out of the Pico, I get a nice PWM signal, and now I'm sort of checking the different components. First, going through the MOSFET driver, so let's check the beginning of the MOSFET driver. So the channel 1 is 5 point something volt, which is correct, and channel 2 is 3.3 volts peak to peak. This is also correct. So now go on the output side of the MOSFET driver. This is what's happening. More sawtooth than anything else. Okay, I removed the capacitor, and now the output looks fine. That means that I have two issues with the PWM section. One issue is that I included a MOSFET driver, but totally skipped the MOSFET. I don't know what happened. Maybe I did this on one day and then did the connections on the other day. I totally forgot just to add a MOSFET. And I don't know what drove me to put a 25 microfarad capacitor between the output and ground. Checking the data sheet, I think I was drunk on that day. Must have been, because I converted 25,000 picofarad into 25 microfarad. That's 1,000 more. However, the isolation as well as the MOSFET driver works as intended, and I can fix the other two issues in the next version.
The relay section was mostly straightforward. The output worked after switching the TVS diode to the correct orientation. The only issue I found here was with the indicating LED. It looks like the routing isn't correct, so it doesn't light up when the relay activates. A small error and probably the first real routing mistake I found on the board. And I did manage to fix it temporarily. For the inputs, I had to reorder a couple of components, including some of the optocouplers. And I think you have seen the solder process enough times. During testing I did overload one channel which slightly broke one of the optocouplers, but after again fixing the polarity of a diode, the input stage worked as intended. So at this stage of the build, pretty much every section of the board actually works. So the voltage converter and the stepper driver outputs work, the PWM outputs work, minus the missing MOSFET, and the relay outputs and inputs work as well. I have a whole list of things that I want to improve in version 2, but this board is more than good enough to get started on the mechanical design and testing of the robot arm itself, which will probably be the topic of the next video. Clearly there are a lot of things that I can improve, but I'm really happy how much of it came together in this first version. I continued populating parts of the board, in particular 2 additional step and direction axes. I also placed connectors and jumper pins, as well as the Pico board, as I would not place any further surface mount components on this version of the board. I do plan on using these Molex style connectors, however right now I don't want to make specific cables yet. So after soldering I temporarily removed the plastic cover to expose the pins to be able to use breadboard cables. This lets me test output functions with real components, such as an integrated stepper as well as a fan. No PWM for now though. This brings me then to my conclusion. During assembly there were some mishaps, but nothing too critical. And version 1 of this controller does enough of what it needs to do that I can already start using it as a platform for the robot arm. Looking at more general improvements and changes that I'm currently working on, the biggest change is that I want to move away from using a Pico 2 board and instead place the microcontroller directly on the board itself. and while doing that, switching to the RP2350B in the 70-pin package, which gives me access to more I/O pins and with that more flexibility as well as expandability. For this, I already ordered a test board. And here I would like to ask you, if you have any ideas for improvements or things I should change or add in the next version, I'd really appreciate your input. See you in the next one.